You are on a late 1880s downtown commercial block. Think an 1890s bank, an office building with a heavy stone cornice and a copper-capped rooftop tower. You have walked past this silhouette 100 times, a finial-like mast ringed with little white buttons and a few thin metal lines that seem to go nowhere. Everyone has a ready explanation, just decoration or just a lightning rod, but if you lean in, those buttons are glazed ceramic insulators, spaced like hardware, not ornament, and the metalwork is not a single rod with a single down lead. It is multiple conductors separated and isolated, like someone expected current to travel without touching the building. So why would decoration need insulation? And why would a lightning rod need distribution geometry? Here is the contradiction. What you are looking at behaves like a system component, not a flourish. And the promise, you can trace this on rooftops, in basements, and in period catalogues and codes, because the city never fully erased the mounting points. Walk the Chicago Loop on a winter afternoon, when the light hits building edges just right, and you'll notice something odd on the commercial blocks built between 1885 and 1900. Above the stone cornices where banks and office buildings meet the sky, there is a recurring silhouette, a copper-capped tower or finial, maybe 8 feet tall, mounted on a cast-iron base with visible bolt heads. Circle the block and you will see it is not unique. 3 buildings in a row carry similar structures, all positioned at roof corners or dead center above the main entrance. The standard story, if anyone bothers to tell it, is simple, Victorian embellishment, maybe a lightning rod with decorative aspirations. But look closer at the metalwork. Those white ceramic buttons ringing the mast are not spaced for visual balance. They are spaced at uniform intervals, roughly 18 inches apart, and each one holds a conductor off the metal frame with deliberate clearance. The conductors themselves, thin copper lines oxidized green now, do not converge into a single down lead. Instead, they run in parallel, each one isolated from its neighbor, each one clamped to its own ceramic insulator. If this were purely lightning protection, you would expect one continuous path to ground. But here you are seeing something else, multiple lines, carefully separated, routed along the parapet with small standoff brackets. The arrangement suggests distribution, not dissipation. In 1892, building codes, installations like these appeared under atmospheric apparatus and auxiliary collection systems, not ornamental metalwork. The insulators were specified as glazed ceramic or glass with sufficient dielectric strength to prevent leakage during atmospheric disturbance. The word leakage implies controlled flow, not emergency discharge. Stand under one of these buildings and trace the geometry. The rooftop mast aligns vertically with something inside, a chase, a shaft, a deliberate pathway through the building's core. The conductors converge toward a single entry point, usually near a corner. The ceramic insulators stop at the roof line. Below that, the conductors disappear into the building, and if you check the basement, you will find a rectangle of cleaner brick on the wall, bolt holes at the corners where something heavy once sat. Ornament does not need a pathway to the basement, but a functional system does. By the turn of the century, New York's early skyscraper district filled in with office buildings that reached 12, 15, and 20 stories. Look at the buildings that went up between 1900 and 1915 near the Civic Center, and you will notice a recurring rooftop feature, a small cupola or lantern structure, usually square, with a copper or slate roof and 4 symmetrical sides. The official explanation is architectural crown, a visual cap to terminate the vertical line. But walk around the building and count the hardware. Each side of the cupola has identical bracket mounts with the same bolt spacing and the same standoff distance from the masonry. Ornament hides its fasteners. Functional equipment exposes them because maintenance requires access. Early skyscraper manuals, documents prepared for building superintendents, included rooftop equipment checklists. These listed ventilation cowls, water tank supports, and apparatus housings. The word apparatus appeared frequently without further specification, as if readers would understand what it meant. Some entries noted ceramic insulators and conductor entry points as items requiring annual inspection. The cupolas themselves show signs of pragmatic function. Their interiors, when accessible, often retain mounting brackets with threaded bolt holes, standardized spacing that implies off-the-shelf components rather than custom ironwork. The brackets face inward and downward, suggesting they once supported something heavy. The floor of the cupola frequently shows a central opening, now sealed, but originally intended for conductor routing between the roof and the building interior. One building near City Hall preserves an unusual detail. A ceramic insulator remains clamped to an iron bracket, with the metal saddle polished smooth from years of conductor movement. The glaze on the ceramic looks almost new, impervious to the soot and weathering that darkened the surrounding stonework. This is not decorative hardware. This was maintained, adjusted, and eventually abandoned in place when its function ended. Standard spacing is a language. It means procurement, someone ordering components from a catalog and specifying dimensions. If these cupolas were purely architectural, every building would have a unique design. Instead, you see the same geometry repeating across different architects, different clients, and different construction years. That consistency points to a shared system, specified according to a common logic. St. Louis, in the decades before World War I, built a row of grand hotels near its rail hubs. These buildings, typically 6 to 8 stories, carried elaborate cornices and rooftop balustrades, but they also carried something less celebrated: clusters of glazed ceramic insulators mounted on iron stanchions along the roof edge. The ceramics are distinctive, spool-shaped with a central groove and flanged ends, glazed in white or pale grey. They are not hidden. They sit prominently on the roofline, visible from the street, and if you can get close enough, you will notice the metal saddles that cradle the conductors show wear patterns. Smooth, polished grooves where copper wire moved slightly over years of thermal expansion. This is the mark of use, not installation. Period electrical supply catalogues, like those from Western Electric in the 1890s and 1900s, listed these insulators by part number. They were sold with specific voltage ratings and dielectric strength specifications, terms that would not apply to decorative hardware. The catalogues recommended mounting heights, clearance distances from conductive surfaces, and replacement intervals based on exposure to weather. These specifications point to function, not ornament. If you examine the stanchions themselves, you will see they are positioned with geometric precision. They are placed at regular intervals, often 6 to 8 feet apart, and aligned with interior wall lines. The conductors they once held would have run along these paths, kept isolated from the building structure, and directed toward a central convergence point. The glaze on these ceramics is remarkable. While the iron has rusted and the mortar has crumbled, the ceramic surface remains intact and glossy. Glaze prevents moisture absorption, which would compromise the insulator's dielectric properties. This was a functional choice, not an aesthetic one. In some buildings, you can still see where conductors were cut and removed, the ends filed smooth, not torn or storm damaged. This was deliberate decommissioning. Maintenance records from the 1920s and 1930s occasionally mention removal of obsolete rooftop apparatus in the same sections that discuss gas line conversions. The apparatus had a name once. It was listed, inspected, and eventually retired according to a plan. San Francisco's turn-of-the-century civic buildings and ferry terminals share a distinctive roofline treatment. Copper conductors, 8 to 12 gauge, run along the roof edge, held off the masonry by small cast iron standoffs. These lines do not end at building corners. Instead, they converge toward a central mast or tower where they all meet at a common junction point. Municipal procurement records from 1898 to 1915 List materials under categories like conductors, insulators, and apparatus housings. The specifications are precise. The record's name, copper wire, tinned, 10 AWG minimum, mounted on ceramic insulators rated for outdoor exposure. The word tinned is significant. A tin coating prevents oxidation, which matters if the conductor is expected to carry current over time. The routing itself tells a story. The conductors follow deliberate paths, bending at consistent radii to avoid sharp turns, which would create stress points. They are clamped at regular intervals to maintain tension. At junction points, they are joined with mechanical connectors, sometimes brass screw terminals, sometimes soldered splices wrapped in insulating tape. This is electrical work performed to standards. If you trace these conductors back to their convergence point, the central mast or tower, you will notice it serves as a collection node. Everything comes together there, and from that point, a heavier conductor or conduit runs down into the building interior. This is network geometry, distributed collection, feeding a central point. It is the same logic as lightning protection, but with a key difference. Lightning rods discharge to ground immediately. These systems route inward to something that regulates or uses the incoming current. Building inspection reports from the era occasionally note these installations as atmospheric apparatus or auxiliary systems, often in the context of safety checks. Inspectors verified that insulation was intact, that conductors were properly supported, and that grounding straps were present at interior entry points. These were safety concerns, not aesthetic evaluations. The pattern holds across building types, ferry terminals, municipal offices, courthouses, and libraries. The same rooftop logic appears in different architectural styles, which suggests the system was not a stylistic choice, but a functional requirement. Detroit's early rail stations, particularly those built in the 19-teens, combined grand public spaces with extensive back-of-house infrastructure. The basements of these buildings were operational centers, and if you examine the walls carefully, you will find evidence of systems that no longer exist. Look for rectangular ghost marks on masonry walls, areas where the brick or plaster is slightly cleaner, with bolt holes at the corners arranged in a standardized pattern. These are cabinet footprints, places where something substantial was once mounted. The cleaner surface indicates protection from decades of airborne grime, and the bolt spacing, often 16 inches on center, matches standard electrical enclosure dimensions from the period. Engineering journals from that era, the 19-teens, documented electrical distribution strategies in detail. Station buildings required multiple power sources for reliability. One recurring item in inventories was listed as atmospheric regulation cabinet or auxiliary storage enclosure, positioned beneath rooftop collection points and connected to those points via vertical conduits. If you align the floor plans vertically, rooftop to basement, you can trace the pathway. The central rooftop tower corresponds to a chase or conduit running through the building's core, often concealed within a masonry wall. At the basement level, this chase terminates near one of these cabinet footprints. The geometry is too consistent to be coincidental. The conduits themselves sometimes remain, though often they have been repurposed for modern wiring. Where the conduit enters the basement, there are often additional grounding straps, heavy copper or bronze bands clamped to building steel and running to a ground rod. This is protective logic, the kind you would implement if you expected sporadic current flow. Grounding is a consistent feature. Salvage patterns explain why the rooftop hardware survived while the basement cabinets vanished. Copper has high scrap value, and electrical components could be repurposed or sold. Rooftop removal requires scaffolding and careful dismantling, and it is expensive. Basement equipment, by contrast, can be unbolted and hauled out in an afternoon. Salvage pressure shaped what remained, so you are left with a partial record. Rooftop hardware may remain intact, interior traces are often visible, and functional components are missing. The bolt holes tell you something was there. The alignment tells you it was connected to the rooftop. The absence tells you it was removed deliberately. Alignment is the clue that links roof to basement. Boston's commercial blocks from the 1890s through 1908 preserve a curious routing pattern. Early electrical service entries typically ran along exterior walls where access was easy, but in many buildings from this era you will find conduits that route inboard, away from the street-facing walls, toward the building's interior core. This suggests the conduits were not retrofits but original installations planned before utility service stabilized. Building codes from the period specified separation requirements for different conductor types. Lightning protection required heavy direct paths to ground. Utility service required accessible routing for repairs. But there was a third category often listed as special apparatus wiring or auxiliary circuits, with its own rules, dedicated chases, insulated from building structure, routed to minimize interference with other systems. Insurance requirements added another layer. Fire insurance underwriters worried about any electrical system that was not utility supplied. Some policies mandated separation between utility and supplementary circuits, with physical barriers and independent grounding. This drove the inboard routing, keeping experimental or auxiliary systems away from the primary electrical pathways. Insurance concerns shaped installation practice. If you map these conduit paths across multiple buildings, a pattern emerges. They do not scatter randomly. They connect rooftop entry points to basement locations, always following interior wall lines, always maintaining clearance from metal framing. The consistency of those paths is an archaeological clue to how these installations were intended to function. The consistency implies planning. Someone specified these chases as part of the building's infrastructure during the design phase. Compare the conduit diameters to known utility service installs from the same era. Utility service for a 6-story commercial building typically used 2 to 3 inch conduit. The inboard conduits are smaller, often 1 to 1.5 inches, which suggests lower current capacity and different usage patterns. The clamp spacing provides another clue. Utility conduits were secured at 8 to 10 foot intervals. These inboard conduits show tighter spacing, 4 to 6 feet, indicating either heavier loading or a requirement for extra mechanical support. So here is the implication. These buildings were pre-wired for something, planned and installed during construction before utility service became reliable. The routing bypassed the obvious paths and created dedicated channels from rooftop to basement. When grid power became standard, these chases were bypassed, repurposed, or abandoned, but the pathways remain. Philadelphia factory office hybrids from the 1890s present all 3 markers in one structure: rooftop mast, interior cabinet footprint, and standardized insulators. The rooftop masts on these buildings are particularly substantial, often 10 to 15 feet tall, mounted on heavy cast iron bases with 8 or more conductor entry points. The insulators are clustered densely, sometimes 30 or 40, in a ring around the mast. This is not ornamental, it is a bill of materials in physical form. Patents from the 1890s and early 1900s describe atmospheric collection apparatus in careful detail. The documents include drawings showing rooftop masts, insulator assemblies, conductor arrangements, and interior control cabinets. The language is technical and includes phrases such as a plurality of elevated conductors, arranged to receive atmospheric electrical potential, ceramic insulators providing high dielectric resistance and regulation means for stabilizing intermittent current flow. The patents do not promise free energy. They describe modest devices for collecting small amounts of current from atmospheric charge gradients, particularly during storm activity. Trade journals like Scientific American covered these installations with cautious interest. Articles noted that atmospheric apparatus could provide supplemental power for specific applications, charging storage batteries, operating telegraph instruments, and powering signal lights. The output was described as intermittent and unpredictable, useful only when demand was flexible. This was not replacement power, it was a situational supplement. If you search patent drawings for insulator cluster geometry, you will find matches to the physical installations still visible on these buildings. The bolt spacing, the insulator count, the conductor entry angles, they correspond closely to the documented designs. These physical details match the drawings. The interior cabinet footprints align with patent descriptions of regulation enclosures containing capacitors, spark gaps, grounding switches, and sometimes primitive voltage regulators. These components manage the incoming current, smoothed fluctuations, provided overvoltage protection, and directed usable power to designated circuits. The cabinet is where regulation happened, so here is the translation. Rooftop point means receiving surface. Ceramic means isolation. Cabinet means regulation and storage. It is a system with defined components, documented in technical literature, sold through catalogs and installed by contractors who understood the principles. The documents do not say free energy. They describe instruments, signaling, and supplemental lighting. Early 1900s office buildings preserve another telling detail: protective hardware at the point where rooftop conductors enter the building interior. Look for heavy grounding straps, braided copper bands sometimes an inch wide, bolted to building steel near the entry points. Nearby you will often find spark gaps or porcelain blocks with two metal terminals separated by a small airspace. This is surge protection. Electrical engineering textbooks from the period devoted entire chapters to surge management. Any system exposed to atmospheric conditions could experience sudden voltage spikes during storms, and without protection, those spikes would damage equipment or start fires. The recommended solution was a layered defense: primary surge suppression at the entry point using spark gaps, secondary protection using grounding straps, and tertiary isolation using fuses inside the control cabinet. The presence of this protective hardware is significant. If the rooftop apparatus were purely decorative or lightning only, it would not need surge protection inside the building. Lightning rods discharge directly to ground. The current never enters interior spaces. Here, the protection is positioned where conductors come indoors, which means someone expected current to flow into the building electrical system. The practical constraints of atmospheric apparatus were well understood. Output was intermittent, dependent on weather, humidity, and local atmospheric conditions. Current levels were low, measured in milliamps to perhaps a few amps during active storms. Voltage was unpredictable. This made the system useful for specific applications, charging storage batteries, operating instruments, providing backup power for signal lights, and running test equipment. The maintenance burden was substantial. Insulators needed regular inspection. Conductors required retentioning. Protective devices had to be tested. The control cabinets needed periodic adjustment. This was not set and forget infrastructure. Safety codes from the early 1900s reflect this reality. They specify minimum clearance distances for atmospheric apparatus conductors, typically 6 inches from grounded surfaces for low voltage installations. They require periodic inspection by qualified persons. So why build it at all, given the limitations? Because before stable grids, supplemental power was better than nothing. If you needed power for a telegraph circuit and utility service was intermittent or expensive, an atmospheric apparatus might justify its cost. It was not perfect, but it was functional. The physical evidence is one thing, the catalog evidence is another. In the pre-World War I era, electrical supply houses published detailed catalogs listing components for atmospheric collection systems. These catalogs treated the parts as standard inventory, no different from switches or generator components. The listings included part numbers, prices, and technical specifications. Western Electric's 1897 catalogue, for example, listed atmospheric apparatus insulators with specific voltage ratings: glazed porcelain bell type rated for 1000 volts dry and 500 volts wet, mounting hardware included. The distinction between dry and wet ratings acknowledges that dielectric strength drops when insulators are moisture exposed. Similar entries appeared for conductor terminals, junction boxes, grounding hardware, and control cabinet components. The ceramic profiles are particularly revealing. Match the insulator shape visible on old buildings to catalog illustrations, and you will find exact correspondences, the same spool form, the same flange lip, the same glaze finish. This confirms that installers were not fabricating custom hardware. They were ordering standardized parts from suppliers who maintained inventory. The system had a supply chain, which means it had a market. Installer manuals from the same period provided mounting instructions, recommended spacing, and wiring diagrams. One manual from 1902 specifies for atmospheric collection installations mount conductors on insulators spaced 18 to 24 inches apart and maintain a minimum 6-inch clearance from the building structure. The tone is instructional. These were standard procedures. The language in these documents is telling. They do not call it free energy apparatus or use grandiose terminology. The catalogs and manuals use workmanlike terms: collection, regulation, storage, auxiliary. The systems are positioned alongside other building infrastructure as practical additions, not as revolutionary technology. Who specified these installations? Architects sometimes included atmospheric apparatus in their plans, particularly for buildings where utility service was uncertain. More commonly, insurers and building inspectors influenced the decision. Fire insurance underwriters encouraged redundant power sources for critical systems, and atmospheric apparatus provided a backup option that did not require fuel storage or mechanical maintenance. So the systems entered buildings through specifications, not rumors. They appeared in bid documents, procurement records, and construction contracts. The fact that we have forgotten what they were called does not mean they were mysterious. Between 1915 and 1940, most US cities underwent systematic electrical modernization. Utility companies expanded distribution networks, standardized voltages, and reduced rates. Building owners upgraded electrical systems, replaced aging components, and increased capacity. This transition provides the timeline for atmospheric apparatus disappearance. The sequence is visible in the physical remains. Rooftop hardware typically stayed in place because removing it required scaffolding and rooftop access. The cost often exceeded the salvage value. Interior components, by contrast, were removed systematically. Conductors were pulled from chases, cabinets were unbolted and hauled away. The conduits themselves were often left in place and reused for new wiring. Permit records tell the story in administrative language. Applications for electrical modernization frequently note removal of obsolete apparatus as part of the scope. Sometimes the permits specify salvage value, listing weights of copper and iron to be recovered. The language is matter of fact. These were routine infrastructure updates. The cause and effect logic is straightforward. As grid reliability improved, the maintenance cost of atmospheric apparatus became obsolete. Why inspect rooftop insulators and maintain control cabinets when utility power was available 24 hours a day at predictable rates? The systems had made sense in an era of uncertain supply, but they became burdens once the grid stabilized. Salvage value accelerated the process. Copper prices rose during World War I and remained elevated through the 1920s. Building owners could recover real money by removing old conductors. Electrical components had resale value to smaller installations or rural facilities still lacking utility service. But rooftop removal was different. It required specialized labor, presented safety risks, and offered minimal return. So owners followed the path of least resistance. They stripped the interior and left the exterior. The result is the pattern we see today: rooftop hardware intact, interior traces visible, functional core missing. Renovation permits from the 1920s through the 1940s occasionally include photographs showing the scope of electrical work. In some cases, you can see before images with rooftop conductors still in place, and after images with the conductors gone, but the mounting hardware untouched. Cleveland's downtown district underwent major retrofits in the 1920s through the 1950s, and facility manuals from this period document a shift in how building components were described. Atmospheric apparatus, once listed in maintenance schedules under auxiliary power systems, gradually disappeared from documentation. By the 1940s, superintendents' handbooks no longer mentioned the rooftop assemblies, or if they did, labeled them simply as architectural details. This relabeling was practical. New building managers had no direct knowledge of the system's functions. Training materials focused on active infrastructure, boilers, elevators, and utility service, and ignored equipment that no longer operated. The rooftop hardware, stripped of its conductors, looked like decorative metalwork. Physical evidence of the transition is visible in the hardware itself. Where conductors once ran, you find cut ends, clean file terminations indicating deliberate removal rather than storm damage. The cutting was methodical. Each conductor was severed near its mounting point, the stub filed smooth, sometimes capped with a protective coating. Brackets that once held conductors were often painted over during building maintenance cycles, further obscuring their function. The paint covered ceramic insulators, iron stanchions, and copper mounting hardware equally. Over decades, multiple paint layers accumulated, and the original hardware became increasingly difficult to read. The vocabulary loss was gradual but comprehensive. Terms like atmospheric apparatus, auxiliary collection system, and supplementary power equipment faded from professional usage as the technology became obsolete. By the mid-20th century, electrical contractors no longer recognized those terms, and no living practitioners remained who had installed or maintained the original systems. This creates a curious situation. Buildings retain physical evidence of systems that no one can name. The hardware is present, visible, and in some cases still structurally sound, but the interpretive framework has vanished. Modern observers see decorative finials and ornamental towers, and they accept those explanations because no alternative vocabulary exists. If the function vanished, what else in the building is misnamed? That question extends to other obsolete systems, pneumatic tube networks, call bell wiring, and gas piping for lighting, all of which leave traces that later generations reinterpret without full context. In preserved historic districts where rooftop alteration has been limited, you can still conduct a systematic check for atmospheric apparatus remnants. The pattern repeats with remarkable consistency. A rooftop mast positioned at the building's highest point, clusters of ceramic insulators along roof edges, and interior traces aligned vertically with the rooftop features. Start with the rooftop. Look for metalwork that rises above the cornice, often copper-capped, mounted on a cast iron base with visible fasteners. Check for ceramic insulators arranged in geometric patterns with consistent spacing. Note whether the insulators show signs of conductor attachment, such as wear on metal saddles, directional orientation, or mounting angles that suggest cable routing. Next, examine the building's vertical structure. Trace lines from rooftop features down through the facade. Look for conduit paths, chase covers, or patchwork repairs that indicate interior routing. In buildings with accessible basements, check for rectangular ghost marks on walls that signal former cabinet locations. Align these basement marks with rooftop features to confirm vertical continuity. Finally, compare across buildings. If atmospheric apparatus was systematically deployed, you should see repetition. Similar rooftop geometries on buildings of the same era and type, comparable insulator spacing, consistent routing logic. Museum collections and archival photographs provide verification. Some technical museums preserve intact atmospheric apparatus installations removed from demolished buildings. These preserved examples offer templates for interpretation, showing how conductors were routed, how cabinets were configured, and how the complete system appeared when functional. The three-step verify protocol works reliably. First, ceramic insulators on the roof. Second, vertical chase alignment between roof and basement. Third, cabinet footprint at ground level. If all three markers appear, you are almost certainly looking at atmospheric apparatus remnants. Once you know what to look for, the pattern becomes inescapable. Walk through any preserved downtown core from 1890 to 1915, and you will spot the markers repeatedly. Not every building has them, but enough buildings retain enough evidence to establish that these installations were common, systematic, and purposeful. The city did not fully erase the mounting points. They are still there, waiting for someone to recognize them. Return to that late 1880s bank building, the one with the copper-capped rooftop tower and the ceramic buttons nobody explains. You are looking at it differently now. The rooftop mast is not decoration, it is a receiving point. The ceramic insulators are not ornament, they are isolation hardware. The missing interior cabinet is not an accident. It is salvage economics. The whole assembly makes sense once you place it in context. A modest, practical system for collecting supplemental power from atmospheric charge used in an era before grid reliability, maintained until it became obsolete, and then partially dismantled when economics favored removal. Compare it to a true lightning rod installation, single conductor, continuous down lead, clear ground termination. It is completely different. The atmospheric apparatus has multiple isolated leads, distribution geometry, and interior routing to control equipment. It is systematic, not singular. What other decorations are just retired technologies waiting for a name? Walk past the old hotels with their roofline ceramics, the office buildings with their cupola brackets, the civic structures with their convergent conductor paths. The hardware is still there. The city does not know what it is looking at anymore, but the evidence remains carved into cornices, bolted to parapets, ghosted on basement walls. The system was real. It was documented, installed, maintained, and eventually replaced by something better. The forgetting was not a conspiracy. It was economics, convenience, and the natural drift of technical vocabulary as one generation replaced another. Obsolete does not mean imaginary, it means a better alternative one.